Hello everyone, this is Kevin Abreu presenting my systems analysis project for hydropower generation. I'm with Professor Alex Squires for class EM566, and sadly I won't be able to make the actual class itself. I had a family member pass away recently, so I flew over and I had to make this recording in advance because I'm actually flying back today, Monday the 10th, to my current living location. So without any further delays, let me start my presentation. So the problem statement, we are actually evaluating a hypothetical young power engineer. He's trying to evaluate some ways to reduce the power consumption bill for his family in Puerto Rico. And it's used for reference. Families or power consumption in Puerto Rico is actually pretty expensive. Average cost is 27 cents. On the mainland US, it's actually 12 cents, so you're paying more than twice the amount. And this specific location is in a mountain-like town, so it doesn't benefit from consistent solar power or solar energy. So evaluating something such as hydropower seems more of a feasible or alternative option, and this is what we're evaluating. Just for reference, values are actually being utilized from a government-owned website as far as the river performance, and the case study river that we are utilizing is Tanama River. So here's a small introduction to hydropower. A hydropower system ranges anywhere from 5 kilowatts to 100 kilowatts. Most of the hydroelectric power comes from providing water into the turbine and the generator system. So this is really important. There are two critical inputs to a hydropower system, and these are actually the values that you can adjust. It's the stream flow that you're providing to the turbine and the head that you're providing to the turbine. So basically, stream flow is the average water velocity. It's in cubic dimensions. And this can be considered kinetic energy being provided to the turbine. The head is actually the drop distance between the highest point of the waterfall into the penstock that actually feeds the turbine. So this is considered potential energy. Customer requirements, these are actually going to dictate the TPM for this specific project. So what do we consider the requirements for this project? Well, the customer and his family has specific power consumption needs that they need to satisfy. So we need a generating system that is able to provide that power without depending on the power authority, which we already know that it's more expensive. And we're required to supply this need, right? So we have determined that the profile for the weekends is to be more power consumption heavy than the ones on the weekdays. And it makes sense. Now, during the weekdays, the kids are in school, the adults are actually at work, or we're expecting them to be at work. During the weekends, everybody is expected to be in the house more time, so it makes more sense for a weekend profile to be more power consumption. This is just to try and be a little bit more realistic with the values that we're getting. The river properties, these are the input criteria, the input performance being provided into the system. So we're talking about the subsystem performance at this point. The average stream flow is actually 78 cubic feet divided by seconds. The head, it can vary depending where you're creating your system, but we can assume 10 feet, and 10 feet is actually a pretty realistic value. The potential power for this river is given by the formula below. Everything, it's basically a way of accounting for the specific weight of water, which is the 62.412 that we're seeing, and 0.7 is friction losses, 0.75 is a conversion factor from horsepower to kilowatts. So we're basically translating everything into kilowatts, and our H, the head, and our Q, the average stream flow, are the values that we can actually adjust. So when we perform the math, we obtain that the maximum power obtainable from this specific river is 46.46 kilowatts. So these are going to be our three design scenarios. So we're going to be evaluating a grid-tied connection with a 3 kilowatt generator system that has batteries. We're going to have another duplicate of this case, but it's not going to have batteries. It's only going to be the grid tie connection and the generator system. And we're going to have a standalone system, no connection to the grid, but it does have batteries, and it also has a bigger generator. This is a comparison between the generator performance and the load requirements. Load requirements are the blue lines. They are identical for this system, and the reason they're identical, they're representing what you're expected to consume on a weekend profile, which is the worst case scenario, for every single hour of the day. The orange and the green lines, they represent the 3 kilowatt and the 5 kilowatt generating performance respectively. So as you can see in the blue line and the orange line, the graph on the left, it performs pretty well. However, at any moment where we have a peak, it's not capable of supplying this power. That's why it relies on a grid type connection and batteries on one of the systems. On the other one, it doesn't have batteries, it's only grid type. On the 5 kilowatt system, you can see that we actually cover most of the peaks. However, you depend on actually utilizing your batteries to supply the remaining power being required. This is just to represent how the system is laid out. At the system level performance, everything is integrated together. At the subsystem level performance, you actually depend on the inputs being fed to the turbine. This determines your subsystem level performance and how it performs as a complete system when you integrate every single component together. This is a functional flow diagram. Basically, it explains how the whole system works. So first thing, your water is being recollected using a penstock from the river. We apply the divergence method, which basically means that you're obtaining a sample of water and then you return it to the river. So the actual net change of water is zero in the long run. You're not taking water away from the river, you're just using it, you're borrowing it so it can go into the turbine and then it returns to the water or to the river itself. Second part, after you provide the water, stream flow and head, which are the two inputs that I mentioned before, they allow your turbine to operate within a specific operational zone. So when it's actually operating, you're generating mechanical power and you're utilizing your generator connected to the turbine to convert this mechanical power into electrical power. When you actually have the electrical power, you're able to feed your house and supply all your appliances and battery chargers and batteries. When we perform the battery calculations, we determine that for the 3 kilowatt system that does have batteries, we only require one 48 volt battery. However, for the 5 kilowatt standalone system, we know that we don't have a grid type connection anymore. For that reason, we actually require to utilize 3 batteries in parallel of 48 volts each. This makes the system much more reliable by itself. However, batteries are really expensive, and we're going to see how that translates into a really expensive project if we went with that approach. So we're going to be performing risk assessment for all 3 cases separately. First one is 3 kilowatts with batteries. The risk assessment tells us that if we start with a risk score of 39, mostly because of the schedule and the cost. Everything lowers pretty drastically after you start considering the fact that you can sell energy to the power authority, that you're preventing accidental blackouts, you have batteries to prevent the blackouts and all that. The biggest problem is that you got to replace your batteries every single 10 years, and then you got to replace your battery chargers every 15 years. 15 years for battery charger, 10 for the batteries. This actually turns out to be really expensive, so we kept the actual schedule and the cost at 11. Here is the actual risk matrix showing that we went from 4.5 to 1.3. The 3 kilowatt system with no batteries, it tells us that at this point we're being a little bit more risky. We can have power blackouts. However, since we don't utilize batteries, this is the cheapest and easiest to implement system. It's actually pretty close to a solar system that doesn't utilize batteries. For that reason, everything drops pretty drastically and the cost of the system drops from a 20 to a 5, giving a final score of 9. And this is our system being populated in the risk matrix. It goes from a 5.5 to 1.2. which is not too bad actually. And this is our last system. It's going to be the 5 kilowatt system standalone with batteries, and this is the risk assessment. So we still have some risk because we can experience power blackouts if the generators and the batteries themselves are not sufficient. However, the cost remains really high. It actually remains at 15. So we were only able to mitigate the risk from 38 to 21 because of this reason. And since we have to replace batteries every 10 years and we utilize 3 batteries rather than 1 because this is the standalone system, it's actually going to be much expensive. And this is the actual risk matrix for this system. So when we perform the risk burn down, we see that the 5 kilowatt system remains at the highest risk because of the cost and the maintenance for the batteries. The 3 kilowatt system actually drops significantly. However, if you're utilizing batteries, it still remains a little bit higher. And the one that doesn't have batteries actually is the one that is the less risky. And it's mostly due to economical reasons. When we perform the cost analysis for the system, we can see that the monthly rates for all 3 systems actually they oscillate a little bit. So on the first row, we're seeing our 3 kilowatt system with batteries, and it's close to $435, which, I mean, you're not saving much in the short term. You're definitely saving a little bit of money in the long term. However, battery replacements are $14,000 every 10 years. So that's really expensive by itself. On the second system, which is the most expensive one, that's actually the 5 kilowatt standalone. And you replace batteries, but we mentioned that we actually utilize 3 batteries rather than 1. So every time that we replace batteries, we're talking about some $43,000 for this system. And the monthly rates are actually $1,000. So that's really expensive by itself. Finally, the last system is the 3 kilowatt system with a grid-tied connection. And this system, since it doesn't replace any batteries, the monthly rate is only $100. $131. So this is really affordable for the customers, and you're definitely reducing the power consumption. We're assuming a 7-year loan and 2.5% interest. We're also assuming that we're going to be replacing batteries every 10 years, as I mentioned before, and that we're also replacing the battery charger. Despite of power credit, which we can see in some of the systems, specifically in the 3 kilowatt with batteries and the grid-tied connection, it's hard to justify the drastic increment in cost due to implementing batteries. Batteries improve the system operational reliability, but they reduce the profit or feasibility under economic terms. So this is really important to take into consideration. And my recommendation, based on the risk matrix, not using batteries in the 3 kilowatt system is the least risky option. Also, based on the cost analysis, the 3 kilowatt system benefits from a low cost. Not using batteries eliminates the original purchase and a replacement every 10 years. Also, remove the cost of the battery charger and the inverter. The 5 kilowatt is a viable option as far as performance. However, its large cost from using 3 48-volt systems, battery systems, to have sufficient storage makes it really unfeasible. And it's basically due to economic restraints. And my personal recommendation will be to recommend to use the 3 kilowatt grid-tied system with no batteries per data and results. Question number 1. What are the 2 inputs that affect hydropower performance? A. Temperature and humidity. B. Stream flow and head. C. Corrosion and humidity. And I'll provide the answer right away. It's actually B. The stream flow and the head are the 2 main inputs to this system. Question number 2. The 3 systems being evaluated had a nominal rating of blank and blank kilowatts. So once again, given a few seconds so people can answer it. And the actual response is 3 kilowatts and 5 kilowatts. Any questions? Sadly, I'm not able to be at the class itself. But if you have any questions, feel free to let me know, send me an email, or let the professor know, and she can contact me as well. And thank you. I appreciate it.